All right, what's up, guys? My name's William Liu. This is my lab too. Um, so, kind of introduce what the lab was. We were tasked with modeling projectile motion, and how that worked was we took a video of our lab group throwing a paper ball across the room. So, the forces working on this, the ball here would be the system, are the forces of drag and gravity, as well as the initial force that the thrower applied to the ball. And then what we did after modeling the motion of that with tracker software is we used GlowScript to create two computational models. So basically simulating how it would ideally, how the trajectory would ideally look. And what we did was one computational model was created with just gravity, and the other one included the forces of gravity and drag, which should have been the most accurate to our actual tracked video. So here's the data presentation. The blue line is the track data of our actual balls, X position and Y position versus time. And then the yellow and red represent the computed models of trajectories. So I'm going to start by analyzing the y position. So we can see how their y trajectories are roughly the same, although the y-intercepts were off. And what caused that is probably the initial y position in the computational models were not equivalent to that of the initial y position of the actual video. And this doesn't necessarily mean that our computational model was off in the y. I think it just means that I didn't fully align the axes. And then for the x position, we can see that they're actually pretty different. The x velocities were pretty different. And all that is saying is that when I put in the x velocity initially, I did not accurately model the x velocity of the ball in the video. I think it's important to note the differences between Model 1, which is just gravity, and Model 2, which is gravity and drag, and that you don't really see that much difference in either the x or y velocities. And I think what caused this is that the drag coefficient of the paper ball through air was relatively low. Hence, the force of drag is negligible, which is why the x position barely changed. So one of the questions that the lab wants me to discuss is terminal velocity. So terminal velocity occurs when the velocity no longer increases or decreases, and therefore the F net equals zero because it's not accelerating. Um, and this will occur when the net force is zero, which is meaning that gravity equals negative drag. And we know that F drag equals the equation on the slide. So basically, how terminal velocity works is once the velocity reaches a certain value, the force of drag will equal the force of gravity, hence canceling out the acceleration. In our lab, we did not reach that velocity. And then another what if is what if the ball were thrown straight up? So if the ball were thrown straight up, the same forces apply, drag and gravity. And specifically in the y-axis direction, nothing changes because either way, it's still falling from a direction, and gravity is still the force acting on it, and drag, so nothing will change. Concluding remarks. So obviously, there are some computational errors with my model, which caused the model and the actual video to be off. There were some. The drag was negligible, like I said earlier. And then code details. Basically, I wrote an algorithm that would iterate the velocity given the force. And then the force would be iterated with the velocity to calculate drag.